All right, picking up right where we left off. I haven't touched a thing. I haven't even moved a muscle. We're going to look at quadratic type equations that contain trig functions. So look down here. This says, it doesn't say 2x squared plus x minus 1. It says 2 sine squared x plus sine x minus 1. It's madness. If it's helpful to you to rewrite the equation in a format that looks like this, you're welcome to. We could let u equal sine x, and that would allow us to rewrite our original equation as 2u squared plus u minus 1 equals 0. And if that makes it look a little bit less cluttered for you, and you'd like to do that, I think it's a great idea. For some of us, making those changes or substitutions and then back substitutions gets to be too confusing. If you can skip it, skip it. That's great. Do whatever works for you. I'm going to solve this equation by factoring. I've done a lot of factoring in my days, so I'm not going to use the AC method or anything like that. I'm just going to sketch out what I think the format of the factored left-hand side is going to look like. I think I'm going to have 1s here, and I need to get a positive u in the middle. So I need to end up with more u's. So there's a 2u, and then with a minus sign here, this will become a minus u, and that's going to work out so that if I FOILed it out and combined like terms, I'd get my previous statement. Nice. So get that minus sign back in there. Now the zero product property says I can set each one of these sets of parentheses equal to 0. So I will do that next. 2u minus 1 equals 0, or u plus 1 equals 0. It's a good thing I'm saying this out loud because the digital pen on this screen, I just don't love it. And look, I try to fix it, it just makes it look worse. All right, let's solve both of these equations for u. On the left-hand equation, I'm going to add 1 to both sides and then divide by 2, which gives me a u value of positive 1/2. The right-hand equation, simply subtracting 1 from both sides, gives me a u value of negative 1. Are those my solutions? No, I'm not trying to solve for u, I'm trying to solve for x. We need to back substitute at this point. So I will write my note, back substitute, and now I can write that the sine of x is equal to 1/2, or the sine of x is equal to negative 1. These are the equations that I need to solve in order to get my final answers. When does the sine of x equal 1/2? Well, that's opposite over hypotenuse, positive first quadrant. That's pi over 6 radians. The opposite over hypotenuse is also positive when I'm in the second quadrant. That would happen at 5 pi over 6. And when does the sine function equal negative 1? In my mind, this is what I'm doing. At pi over 2, it equals positive 1. At 2 pi over 2, it equals 0. At 3 pi over 2, it equals negative 1. There it is. 1 pi over 2, 2 pi over 2, 3 pi over 2. And these are my 3 solutions that I would type in separated by commas. I probably don't have to put the x equals. I probably don't have to put them in set braces. Just type them in. This next equation, I'm trying to pick up the pace a little bit. Let's solve it for secant squared x. Add 2 to both sides. Keep the 4. Equals 2. Divide both sides by 4. Which reduces to a 1/2. And now I'm going to take the square root of both sides. Secant x equals 1 over the square root of 2. Now, how did I get from here to here? I took the square root of both sides, which means I took the square root of the numerator. The square root of 1 is 1. I took the square root of the denominator. That's a root 2. but I'm leaving it like this. If you've jumped the gun and already rationalized your denominator, you may have gone too fast, because the secant of x is the reciprocal of the cosine. So I'm going to take the reciprocal of both sides, however you want to note that. I like to put an exponent of -1. That tells me I'm taking the reciprocal. That's my notation. Use it if you want to. If you want to take the reciprocal of both sides of the equation, write it out, whatever you need to do. That allows me to rewrite this as the cosine of x as equaling the square root of 2 over 1. And honestly, I made a bit of a mistake, a mistake by omission. Remember that when you take the square root property really says I should be putting in a plus or minus. So let's put in a plus or minus here and a plus or minus here. Now, what's the square root of 2? It's approximately 1.4. What's the range of the cosine function? The range of the cosine function goes from -1 to +1. So, is it possible that the cosine function could output a value of +1.4 or -1.4? I don't think so. And when you get into a situation like this, the first thing that I do anyway is I immediately go, at the moment it looks like the solution is no solution. No solution freaks me out. So I go back and I check my arithmetic, just walk through it one more time, make sure I copied the problem correctly onto my scratch paper, stuff like that. So I'm looking back, I added 2 to both sides, that took me to here, that looks good. Divided both sides by 4, that looks good. I reduced my fraction correctly, that looks good. I took the square root of both sides, square root of 1, square root of 2, that all looks okay. I put the plus or minus sign. Secant reciprocal is cosine, that's true. Did I correctly flip this thing? I did. I think we did everything correctly. So the solution to this problem, or this equation, is that there is no solution. And it's good that we see an example problem where we have, in this problem, we had 3 solutions. In a previous problem, I think in the previous video, we had 4 solutions. And we had 1 solution instead of our typical 2 solutions. And here we've got no solution. Here's another type of equation. It's not a quadratic, but it's another factorable equation. This equation has 2 terms. Those 2 terms contain a common factor. They both contain a factor of cosine, so I'm going to factor out a cosine. Let's write this as cosine x times 1 minus 2 sine x, and that does still equal 0 on the right-hand side. The zero product property says I should take these 2 things on the left-hand side and set them equal to 0. Let's do that. Cosine x is equal to 0, or 1 minus 2 sine x equals 0. Notice we didn't need to do u substitution on this one. In the previous problem, in order to make the factoring process a bit easier, we used u substitution. Here we don't really need to do that. Let's just pull that cosine out of there. The thing that I see most frequently is that some of my students forget to put the 1 right here because they think that cosine divided by cosine cancels out and just evaporates and turns into nothing, but it doesn't. Anything divided by itself is equal to 1, so don't forget to put that 1 there. The right-hand equation, let's just go a bit further with this one. I'm going to add the 2 sine x to both sides, so that 1 stays on the left-hand side. The 2 sine x is now on the right-hand side. Then divide both sides by 2, so we get a 1/2 on the left, and a sine x stays on the right. Nice. So let's solve this equation and this equation. When does the cosine of x equals 0? That happens when x equals pi over 2 and 3 pi over 2. When does the sine of x equal 1/2? We've seen this statement multiple times between this video and the previous one. That happens when x equals pi over 6 and 5 pi over 6. which now makes me nervous because I feel like the last time I wrote pi over 6 and 7 pi over 6, but it should have been 5 pi over 6. So in this problem, we do indeed have 4 solutions. There they are. And I'm just going to take a quick run back up to the top of this page and see if my memory is deceiving me. Nope. We're good. I did write 5 pi over 6 that time also. Nice. All right, there you are. Those are the 4 solutions to this problem. So a different type of a factorable equation. Let's see what else we have that's in this strange realm of working with equations. Oh, here we go. We have even more sort of legwork that we have to do in the beginning of this process before we can write up a solution. This equation has cosines and sines in it. And that's a problem. It's not going to allow us to factor this very easily. We have another visitor I've got to let in. You have a little FOMO there. Are you? Yeah? Okay. You come say hello, or are you just here to mess things up? Come here. Come say a quick hello. Ooh. Oh my gosh. I think I'm going to have to stop feeding you. Just say hello. There she is. There's the loon. There's that beautiful baby. You want to do some trig equations with us? She's not even willing to look at the camera. She's disgusted. I don't blame you. Say hello. You're so big. Just look at her. She's giant. All right. Oh, get down there. We need to either change the cosine stuff or the sine stuff into... we need to change one into the other or the other into the one. And when I see cosine squared, anytime I see any trig function squared, my mind immediately goes to the Pythagorean identity. The other place that your mind should go is to here. This formula sheet might have some options for us. I'm seeing cosine squared x. Let's see, sum and difference, no. Sum and difference, no. Double angle. Oh, double angle's got some cosine squared. I don't think that's it. Could we power reduce this? I don't think we want to do that. I don't think the power reducing formula is the only one jumping out at me. Except cosine squared, when you power reduce it, ends up as a 1 plus cosine 2 theta. Well, for one, it ends up as a cosine function still, so that's not good. And the angle measure has to get doubled, so I don't think that's it either. So I'm going to use a modified version of the Pythagorean identity in order to change that cosine squared. Let's put a little note over to the side that says sine squared x plus cosine squared x equals 1. I'm going to solve that for cosine squared. So cosine squared x equals 1 minus sine squared x. And it's this cosine squared x right here that's going to get replaced by the 1 minus sine squared x. And when I make that exchange, that substitution, I'm going to use parentheses. And in this case, it's important that we do that. So let's do it. Here's the 2, here's the parenthesis, and my 1 minus sine squared x, close, minus sine x was already there, minus the 1 that was already there, still equals 0. Okay, now my equation has all sine stuff. I like that. Let's distribute the multiplication by 2, combine like terms if possible, and then we'll go from there. We can't anticipate everything, so let's just deal with what's in front of us. And if you want to put a little note over here, dist for distribute, you can. Pythag for Pythagorean theorem. You could have a little arrow back in here that says substitute or sub. Put as many notes in as you would like to have that articulate the process that we've gone through in this problem. So now we're distributing. Oh yeah. All right, so that's 2 minus 2 sine squared x minus the sine x that was already there minus the 1 equals the 0. Okay. Well, I see the 2 out here and the minus 1 here, so we could combine like terms. Let's do that. CLT for combine like terms. Negative 2 sine squared x, that didn't change, this doesn't change, and then a 2 minus a 1 makes a positive 1, still equal to 0. Okay. What I don't like about this equation, and I didn't like about these types of equations when I was in college algebra or intermediate algebra, any of the algebras, I don't even like it now. I don't like that it has a leading coefficient of negative anything. If I could divide the entire equation by -2, I would. Then it would say 1 sine squared. However, this would become a positive 1/2. This would become a negative 1/2. I don't like those fractions. So what I am going to do is multiply or divide my entire equation by -1. And again, I did that so that my leading coefficient became positive. Now I'd like to factor this. This is looking strangely familiar. 2 sine squared plus sine x. Does anyone else think this looks familiar? How far back do we have to go? Too far. Too far. I'm feeling warmer. I'm getting warmer. Oh, I don't know. Maybe it's a pipe dream. Hey, here it is. 2 sine squared x plus sine x minus 1. So it's positive, positive, negative. Positive, positive, negative. This is the same darn equation. Unbelievable. All right, well, I should have taken note of what those solutions were in the previous problem, but it doesn't hurt for us to practice this again. I'm going to use some u substitution. I'm going to write this as 2u squared plus u minus 1 equals 0. And then we can factor 2u minus 1 and a u plus 1 equals 0. Then we can set each one of those factors equal to 0. 2u minus 1 equals 0. U plus 1 equals 0. And then we can back substitute. Let's replace those u's with sine x's. Oops. It should say 2 sine x minus 1 equals 0. Or sine x plus 1 equals 0. Solve both of these equations for sine x. And we said that the sine of x is equal to positive 1/2 when x is equal to pi over 6, or 5 pi over 6. That was the one I had to go back and double check even. And sine of x is equal to -1. I told you before, I'll tell you again because I like the visual. At pi over 2 it equals positive 1. At 2 pi over 2 it equals 0 again. And at 3 pi over 2 it equals -1. So here x is equal to 3 pi over 2, and these, again, are our 3 solutions. So a different starting point, a different first half of the process with some substitution thanks to the Pythagorean identity, and then after that, the process was the same as it was in a previous problem. But this initial part of this problem is what you need to really be taking note of and sort of training your mind to look for the possibility of using, in this case, the Pythagorean identity in order to do some substitution, or potentially using one of the other formulas or identities from your formula sheet in order to make some substitution so that we have, in this case, what we wanted, which was consistency. We had the sine function appeared throughout the equation instead of, as we had initially, a cosine function and a sine function mixed into one equation. Typically not desirable. These problems go on, right? I could hang out with you all day and solve these problems. You need to practice these and be wrestling with these by doing homework assignments. with your formula sheet alongside of you. I'm looking off camera because I'm looking at my formula sheet. And this problem has a cosine 2x and a cosine x. I see that cosine 2x and bells and whistles go off. It says double angle to me. And about a third of the way down my formula sheet, I see the double angle formula for cosine 2 theta. And that's equal to cosine squared minus sine squared. I don't love the idea of replacing this with cosine squared minus sine squared because I'd have a sine squared, but I don't want a sine squared. I've got cosine in this problem. I don't want to have a mix and match in the same equation. So I note that over on the right-hand side of my formula sheet, there's a little box that's there that says alternate cosine 2 theta formulas. And the, excuse me, the first of those formulas says that the cosine of 2 theta, but since this problem uses x's, I'm going to write it as an x. It says that the cosine of 2x is equal to 2 cosine squared x, or theta, minus 1. So that's the substitution that we would want to happen. The cosine 2x in the original equation is the same as this cosine 2x, so it's going to get replaced with this content, and you should be off to the races. Make that substitution, combine like terms, the positive 1 and negative 1 are going to cancel out, and then you're going to end up with a problem that matches up with one of the types of factoring that we have done previously. And I will tell you that it is this type of a factoring problem. Not one of the factoring ones where it's a reverse foiling. It's a factoring problem where you're taking a common factor out of both terms. All right, so have a go at that one. Make the substitution, do the factoring, crank out a couple of solutions. What's another type of problem that you might see? There's this one. This one's really confusing because it's got a sine and a cosine in it, which we know that we don't like. We don't like the mix and match. But I don't see any way that I could do any substitution in this problem. If it were sine squared plus cosine squared, that would be the Pythagorean identity. That I would love. And it would equal 1, but alas, it just says sine plus cosine. So I'm grabbing my formula sheet, and I'm just kind of thinking, and I don't know. Could I? What would happen if I did square both sides of the equation? I'm going to put the formula sheet down. Let's just force it and see what happens. I'm going to raise both sides of my equation to the second power. And remember, that means I'm taking this whole quantity and squaring it. Which means on the left-hand side, I need to FOIL and combine like terms. I'm just going to do that in my head, but if you need to write it out, see if you get what I get. You should get sine squared x plus 2 cosine x, well, I'm going to write it as 2 sine x cosine x. That's the O and the I terms. When you combine like terms, you should have sine x cosine x plus sine x cosine x, which gives you 2 of them. And then the L in the foiling process should give you a cosine squared x. Squaring a negative 1 on the right-hand side of the equation gives you a positive 1. If you need to pause to get caught up, pause to get caught up. But what I'm seeing here is a sine squared plus a cosine squared, which I know combine by the Pythagorean theorem to equal positive 1. So I'm going to put a little note over here that says Pythag. And by the Pythagorean theorem, I'm going to write this equation now as 2 sine x cosine x plus 1 equals 1. So again, sine squared x plus cosine squared x turned into a 1. That's this one. There we go. And now I'm going to subtract 1 from both sides of my equation. 2 sine x cosine x equals 0. Then I'll divide both sides by 2. I don't know why I'm switching pen colors for my annotations, but I am, so I'm sticking to it. Divide both sides of your equation by 2. Sine x cosine x equals 0. When you have a product of two things and the result is equal to 0, that's the zero product property. The only way to make that happen is if the first thing is equal to 0 or the second thing is equal to 0. When does sine x equal 0? I'm imagining the graph in my head. It's coming out of the origin, so that happens at 0. It crosses the x-axis again when x is equal to pi. Cosine is equal to 0 1/4 of the way through its period and 3/4 of the way through its period. And those are the 4 solutions to your original equation. Should you go and take these x values one at a time and plug them back into the original equation just to make sure? It wouldn't hurt. I don't think I've ever done it. Now I feel obligated to do it. Why don't I just pause real quick and plug those in my head? Well, that didn't take very long. Are we recording again? Yeah, we are. Plug in an x value of 0. Well, the first thing you should do is erase the box that you just put around. Oh, I hate when that happens. I don't know why it won't just erase my rectangular box. It's taking me way back too far. All right, so these are proposed solutions. Maybe I'll put a circle around them as proposed solutions, and then we should do a test. What's the sine of 0? Picture the graph. It's 0. What's the cosine of 0? Picture that graph. It's positive 1. What's 0 plus 1? 1. Does 1 equal negative 1? No, it does not. So let's check. X equals 0. If we check x equals 0, we just said that we get 0 plus 1 equals negative 1, which is false. So the x value of 0, we're going to throw that one out. Let's also check an x value of pi. The sine of pi is equal to 0. The cosine of pi is equal to negative 1. That one's true. Let's check x equals pi over 2. Sine of pi over 2 is, my brain's getting tired, positive 1. The cosine of pi over 2 is 0. That's false. And finally, let's check x equals 3 pi over 2. The sine, isn't that what's first? Yep, there it is right at the top of the screen. The sine of 3 pi over 2. 1, 0, negative 1. And the cosine of 3 pi over 2, 0, negative 1, 0. That is true. Boy, am I glad we did the check. That is one of our solutions also. So if you want to write down separately, solutions, maybe we'll just put pi, comma, 3 pi over 2. If you want to put them in set braces, you may. I'm just going to put them in the box. And oh, I feel like we dodged a bullet on that one. Wow. Only 2 solutions. What compelled me to check my solutions, you might be wondering. The very first thing we did in this problem was square both sides. And when you square both sides, things that should have turned out to be negative ended up becoming positive because we squared them. And in fact, we were really squaring the equation originally in order to try to force the ability to use the Pythagorean theorem, which worked. Except notice that the right-hand side, which was originally negative 1, became a positive 1. And then we carried that through and really used that positive 1 throughout the problem. That's what allowed us to get the 0 on the right-hand side, right? We started with a -1, and then the 1, and then the 1, and that turned into a 0. And the 0 was really a big component to being able to set those two factors equal to 0. That just set off a tiny little sort of red flag in my mind that said, hey, maybe we should do a check. And again, good thing we did. All right, this problem says find all the solutions on the interval, approximate solutions 4 decimal places. Yeah, you could, oh, I hate these problems. For starters, take the inverse sine of both sides. If you want to put your calculator in degree mode, you could do that. Take the inverse sine, and remember that the range of the sine function is, what's the range of the inverse sine function? It goes from negative pi over 2 to pi over 2. So I'm picturing it in my mind. Yeah. So the inverse sine function is only going to spit out an answer, a degree measure in this case, because I'm going to put my calculator in degree mode, that's somewhere in the 4th or 1st quadrant. I'm hitting mode, I'm using my TA84 at the moment. You could very easily still do this in a scientific calculator. All right, so I'm in degree mode. I'm going to take the inverse sine of 0.7392. And I got an answer of 47.6633. So x equals sine inverse of 0.7392. X approximately equals, I said, 47.6633 degrees. So that's one of our answers, and that is rounded. It was 66331, so I rounded to the 4th decimal place. And then how are we supposed to turn that into another solution that's on the interval from 0 to 2 pi? And it's saying 0 to 2 pi, so maybe I really should have answered that in radian mode. I can give you that solution real quick. I'm changing back into radian mode. I'm scrolling back to my previous input of the inverse tan, and I got 0.8319 rounded. So I'll say or 0.8319 radians. And then how are we supposed to convert that into another answer that's on the interval from 0 to 2 pi? Visually might be a good way to go if you think about these things like I do. Got a fuzz on my screen and it's distracting me. There we go. Uh, 47 degrees is almost right in the middle of that first quadrant. So this could be my, oh, Sophie's walking on my splitter here. Let's see. There we go. So that's my first x value. And then I know that sine is positive in the 1st and 2nd quadrants. So really, there should be another angle measure available over here. These triangles should be identical, and this angle measure here should be x, which means that in order to get my hypotenuse into that location in the 2nd quadrant, I have to do that much rotation. And that much rotation is x degrees short of a half of a rotation. So my other x values would be 180 degrees minus the 47.663. So 180 minus 47.663, that is 132.337. Oh, I didn't type in. There we go. 132.3367. And if we did that using radians, instead of 180 minus, we would want to do pi minus 0.8319 equals, and that is, all right, or 2.3097 rounded. So however you want to put boxes around those. This is degrees, this is radians. Right, so either these are your two answers in radians, or, ugh, this is going to get ugly. I can't do it. I can't put boxes around those. Or we'll go highlighter. These two would be your answers. Little tricky, definitely tests your ability to sort of think your way around the unit circle, and it brings back the all students take calculus in order to make sure that you're getting that second solution in the correct quadrant. You have to be mindful of the range of the restricted sine function, or inverse rather, sine function. So testing a lot of our skills on that question there. That's a good one. And finally, this one, 3 times 3 is 9. 1 times 9 makes 9. Negative 9 plus positive 1 makes negative 8. Negative 9 times positive 1, or plus positive 1. No, times negative 1. Anyway, you can use the AC method in order to factor this thing. Let me do that without the babbling. Or you could just sort of go right into it. Set up a little framework for it. I'm going to go with my 3 cosine x here. I'm going to need a cosine x here. I'm going to need the 3 cosine x to multiply by a negative 3 in order to get negative 9 cosine x's. And then I'll have to add a positive 1 cosine x back to the negative 9 cosine x's in order to get that negative 8 cosine x. And I think this is a fine factored form. If we set these equal to 0 and solve for cosine x, we will get cosine x equals negative 1/3, and cosine x will equal 3. There's an intermediate step in there that I didn't write out where I set each one of those things equal to 0 and then solved them for cosine x. Is it possible that the cosine of x as adjacent over hypotenuse could equal negative 1/3? Absolutely. And that would happen. Cosine is negative in the second and third quadrants. So you could take the inverse cosine of both sides of that equation and get yourself an initial solution, which would be in the second quadrant because of the range of the restricted cosine function, or I should say the range of the inverse cosine function. And then, actually, that one's kind of fun. Where are we? 38, going on 39 minutes. That's all right. Let's do this one. So I'm going to take the inverse cosine of both sides. So let me write down that x is equal to cosine inverse of negative 1/3. I'm probably going to lose my screen here in a second. So x is equal to, let's do this in degrees, just because they're a little bit more friendly. Let's try this. Let's see, mode, come down to degrees, quit out of there, and I'm going to do inverse cosine of negative 1/3 equals, and I got 109.47 degrees. So that's definitely into the second quadrant. And again, I got 109.47. And if it's helpful to you to draw a diagram of that, I would diagram the second and third quadrants there. And 109 is almost 20 degrees larger than 90, so it's pretty high in the second quadrant. And if you want to maybe do something like this and put a little X on it. You could get your arrow going there. The next step would be to figure out how large this reference angle is. Then we could double that amount and we would have the size of let's see, we need to be down here again for the cosine to give us -1/3, because here's the -1, here's the hypotenuse of 3, here's the other hypotenuse of 3. So again, this reference angle and this reference angle are going to be the same size. So we could do 180 minus the 109.47 to figure out the size of the reference angle, and then add that amount to 180, and that would take us down into the third quadrant. So let's do that quickly. I'm going to do 180, and we could even say like reference angle equals 180 minus 109.47, which is equal to, let's just do it in our heads, shall we? How about 70.53? So that looks pretty accurate. You should double check that in the calculator. And now I should have written all of that in purple, because that's that reference angle. It's also this reference angle. So I'm going to use my original 109.47 degrees that swung me into the second quadrant. I'm going to add my 70.53 degree reference angle twice, and that's going to push my hypotenuse farther around deep into the third quadrant, and we will have our second solution. Do I still have that number on my screen? There's the 109.47. I'm going to do the 180 minus my answer just to confirm. It's actually 70.528, which does round to the 70.53, so I was using a rounded value there. I'm going to take that number that's on my screen, the 70.528, I'm going to double it, so times 2, and I'm going to then add the inverse cosine of the -1/3 again. That way I'm working with all exact values, and I get 250.528. So maybe 250.53. Let's see. X sub 2, or I don't know how you want to call this as your second solution, is equal to. We could go back and title these as x sub 1, I suppose. x1 and x1. x1 is equal to x1 plus 2 of our reference angles. So that is the 109.47 plus 2 times the 70.53, which gives us our second final answer of 250.53, I'm calling it. Oops, needs to be a 5 in there. 0.53. Nice. I had put a circle around the 109.47 before. I'm going to go back and erase that and make it a box, because that was a final answer. That was a good angle measure. And then I'm going to put a box around this 250.53 degrees. I'm going to get a little degree mark on it. There we are. It's not much of a degree mark. So those are two solutions. Those are the two solutions that are within one full rotation between 0 and 2 pi, or in this case, I chose to do it between 0 and 360 degrees. And then finally, we can come back up here and address this second equation that says that the cosine of x is equal to 3. I knew we weren't going to have to do this much with it, do very much with this equation, because I recognized right away that the cosine of x here is outputting a value of 3, which is larger than 1. 3 is larger than 1. Cosine has a range that goes from -1 to +1. This second little equation right here has no solution because 3 is not in the range of cosine. No solution. I'm not putting a box around it because really my final answers are these other two values, the 109 and the 250. Whew. That was a good one. You might want to watch that one a couple of times. Try to work that problem out on your own. See if you can make your way through the thought process. Do the calculations on your own. Use whatever calculator it is that you're supposed to be using. Do the problem with both calculators at the same time. Put your grapher and your scientific out and make sure that you're comfortable using the input methods and things like that on both of your calculators. The graphing calculator is so nice for typing that stuff in. If you, however, have to type in that work on this scientific calculator, which is the TI-30XA, the input process is considerably different. So please also practice it on that calculator. If you have the I don't know what it's called, TI-30X2 or something like that, it's got a Roman numeral 2 on it, the input process on that calculator is pretty easy. But especially if you have the TI-30XA, make sure you practice inputting this, especially the inverse trig functions into that one. Okay, we did it. We made it to the end of it. A two-parter. I don't think I've done any of those before. So if you made it all the way through both of those, I'm applauding you in my mind. And I wish you all the best working through some homework assignments on this stuff. Remember, some of this stuff is a little weird. Some of this stuff is quite new. We're getting no solution, 1 solution, 2, 3, 4 solutions, infinitely many solutions. You've got notation that you need to worry about in terms of your n value being a member of the set of integers. You're using set builder notation, which you don't usually use. Sine and cosine are probably going to be requiring the set builder notation to have 2 statements in it, whereas the tangent or a cotangent function is going to give you only 1 statement where you're adding integer multiples of pi. So there's a lot of little details for you to contend with here. So make sure you're working a really good sampling of example problems in order to prepare for a quiz or an exam so that you are as well prepared as you can be for all eventualities. Boy, did that sound like a lecture. All right, enough of that. Thanks again for joining me. Like, subscribe, and go do some homework. Take care.